Okay, let's continue our discussion of probabilities, and we're going to expand upon it using this simple example. So here I have a container that has 4 red rocks, 7 blue rocks, and 10 white rocks. What is the probability of randomly selecting from this container 1 red rock? So to find the probability of 1 red rock, you're going to reach into this container, you're not really looking at what you're grabbing, and you pull it out and you go, oh, look, it's red. Well, the number of events there is still 4 rocks that are red out of all of the rocks. So here we have to add them all up. So the denominator is going to be 4 plus 7 plus 10. So this turns into 4 out of 21, if I added that correctly. Okay, and I'm going to just leave it like that, 4 over 21. What's the probability of selecting a blue rock out of this mess? Well, that would be the number of blue rocks divided by all of the rocks that are in the container, the entire outcome. So this would be, it's not going to be 4. There are 7 blue rocks out of 21. So that would be the probability of selecting a blue rock out of this container. And then the probability of a white rock is going to be the number of white rocks, which is 10 out of 21. Now, the reason I'm looking at each individual probability is, number one, there's only red, blue, and white rocks in this container with these specific numbers. So these are all the possible ways of pulling a rock out of this container. It's either going to be red or blue or white. So if I take this and I say, what is the probability of selecting a red or a blue or a white, they are mutually exclusive, so we really only need to add the probabilities together. So this is going to be the probability of it being red plus the probability of it being blue plus the probability of it being white. And if you take a guess here, when I added 4 plus 7 plus 10 before, it was to come up with the total number of outcomes. And because the common denominator here is 21, I'm just going to add 4 plus 7 plus 10, which gives me 21 out of 21, which is equal to 1. So I am guaranteed to be pulling one of these rocks out of the container, so this probability of 1 has a word associated with it. It is absolutely certain that I'm going to pull a rock out of this container. The other thing that's interesting is there is no way to get the probability to be larger than 1 because these are all the possibilities. So the maximum probability value is always equal to 1. There is no way to get anything larger than 1 out of probabilities. This leads into a few other things, though. For instance, if I said, what is the probability? This is a cool little question, because what if I didn't go looking for probability of blue, probability of white individually, so I could look at it that way? Another way of answering this question is I know the sum of the probabilities is going to be 1, and I know the probability of being red, probability of being red is 4 out of 21. So I can find the probability of not red really quickly, because if you're not red, you're blue or you're white. So it's either going to be the sum of 7 plus 10 over 21, 11 out of 21, or we can look at it this way, 1 minus the probability of being red. This is known as a complement. Finding the probabilities of a complement. The complement, of course, being not red, so you're going to go 1 minus the probability of is red. So this would equal 1 minus 4 out of 21, which if you got a common denominator of 21 over 21 and you subtracted 4, you would end up with 17. I'm sorry, I said something else earlier, but it would be 17 out of 21. And if you add 7 and 10 together, you get 17 out of 21. So this idea of complement, of subtracting your probability that you know from 1, gives you all the ones that are not that 1. So we're going to use that a lot. Being able to recognize complements in a probability statement sometimes can be kind of tricky. So I wanted to give a general outlook of what you're going to be looking for and what a complement will be able to find. So if your statement is, probability of a red rock or something like that, then the complement obviously is going to be not red. All the colors that are in the container still that are not red would be its complement. And that's kind of what we were talking about just a little while ago. But sometimes it gets a little bit, stranger. Like if I have red or blue, and these are just examples, words, red and blue, they could be anything. So you got to be really careful with that. These are just events of probabilities, and if the word or is in between it, then what you have to go to complement it is to say not red, and this is important. The or actually turns into an and then this is not blue. So if you have or on one side, it turns into and for the complement side. If you have positive red and positive blue, then it becomes not red and not blue on the other side. So that's one important feature. Another important feature is if you have something like all questions correct, what's the probability of getting every question on a test correct? And we're looking for all of them correct. So the complement of all is not none. You can't go from a test that has all correct answers to a test that has all incorrect answers. That's not going to be its complement. So its complement is going to be at least one is wrong. So if you didn't get 100 on the test, you got something else. So if you get at least one wrong, then you're not being perfect, but it doesn't tell you much else other than it could be any score below 100. So one of them is I got 100 on a test. The other one is I got something other than 100 on a test. So the opposite of all, or the complement of all, is always going to be at least. And over here, because the question is correct, on the other side we need to change it to wrong. So these are three of the main ones that you're going to see, and we have to be able to find their complement probabilities. So let's talk about complement probabilities. Let's take the all questions correct. So for example, if the probability of all questions correct is 0.015. Now I'm writing it as a decimal, so this is the same thing as 1.5%. If you multiply by 100, it changes it to a percent. Now you got to be careful. I'm going to talk about both of them and how the complement works for a percent version of probability and a decimal version of probability. All right, so let's start off with the decimal version of probability. What is the probability of not getting 100 on this test? So if the probability of getting them all correct, which is, by the way, getting 100, is 0.015, we're going to call that the probability of the event. So it's 0.015. So the probability of its complement is going to be denoted this way. It's a little dash next to the E. So this is the probability of the event's complement, which is going to equal 1 minus 0.015, which is equal to, oh, I don't want to mess around with it, 1 minus 0.015985. So this is 0.985. So the probability of not getting 100 is actually quite high. Now, if we're talking about the probability, let me change colors here, that one. If we're talking about the probability of the event being its percentage, 1.5%, then the probability of the event's complement is very similar. It's just you're going to have to do 100% minus 1.5%. And the answer is going to be 98.5%. It's just, instead of subtracting from 1, now you're subtracting from 100. So that's how you're going to use complements when your statements are one thing and you're looking for the complement side. So generally what will happen is the probability will ask you for the complement, and you have to go find the probability of its statement first before you can even find the probability of a complement. All right, now it's time to talk about, instead of, the probability of a single thing happening, but the probability of multiple things happening. So I've set up a very simplistic experiment here. I have a container that has 2 red rocks and 1 blue rock. And I'm curious about what the outcomes of the experiment are, because if I can figure out what the outcomes are, then I also can figure out certain probabilities based on this outcome. All right, so before we even start talking about this, though, there's 2 possibilities that can exist. This can be done like the lottery. If you've ever watched it on TV, they take the tennis ball that shoots, or tennis ball, the ping pong ball that shoots up with a number on it, and they set it off to the side. So that is called without replacement. That is one way to do a lottery. Another way to do it, which would make it even much more difficult to win, would be if they took that ping pong ball and put it back into the mix and let another number be exactly the same. So that is what's called with replacement. So before we can do one of these questions of multiple selections, we have to know if we're dealing with a without replacement or with replacement. Without replacement, this becomes known as dependent. And with replacement, it becomes called independent. And dependent in the sense that when you remove something from an experiment, it changes all the probabilities. Where if we put it back, nothing's changing, so it's quite independent what's going to happen. All right, so let's treat this in both cases. We'll do it without replacement first, and then with replacement second, and I'm going to use something called a tree diagram to figure out what the possible outcomes can be and how many there are. So what we're going to do is we're going to have our container here, and then a tree diagram basically depicts your probabilities. So these 3 branches would be your first pick. So in your first pick, when you reach your hand into that container, you have 3 rocks. So you could either pick the first red rock, the second red rock, or the 1 blue rock. All right. Now, this is without replacement. So now we've taken that rock, whatever it was, and set it off to the side. So if I'm on this first branch, I have set aside a red rock. So all that's left in the container is 1 red rock and 1 blue rock. So after I pick the red rock, I could pick the second red rock, or I could pick the blue rock. And the same thing goes for the second red one, because I still have 1 red and 1 blue. Now, if I pick the blue, then the only thing left are 2 reds. So we're going to either pick the first red or the second red. So this becomes all the possible outcomes. I'm kind of separating the reds like I did the dice. so we can recognize which one is which, though they're both numbered, and that's all we cared about. So the outcomes is you either get a red red, a red blue, a red red, a red blue, a blue red, and a blue red. Okay. So that would be the without replacement. We take it off to the side and we change our probabilities. Now, if we do it with replacement, our branches for the first one stay the same. We're still going to have 3 branches. It'll be red, red, and blue. And then the problem is we're going to take that rock and put it back into the mix. So we always have 3 more rocks. So each one of these is also going to have red, red, blue as 3 of its possibilities. So red, red, blue, red, red, blue, red, red, blue. And therefore, these outcomes are red, 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 blue, and then the same thing again. And then finally, blue, red, and then, oh no, that's possible. Blue, red, and blue. Put it back in the mix, and blue again. So one thing to notice is the number of outcomes is different. On the left-hand side, there are only 6 outcomes. So if we look for the total is 6. And over here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So here our total outcomes is 9. And there's a reason why this is happening. All right. So if I say, what's the probability of selecting a red first and then a blue second under the without replacement, the dependent set, red first and blue second, that happens here, 2 times. So this would be 2 out of 6, or better known as 1/3. And red first and blue second over here with the independent after we replaced it, red first, blue second. Red first, blue second. That would be 2 out of 9. So even the probabilities are different, just slightly. So where are these numbers coming from? So we can think of it this way. We can say if I'm looking for the probability of red first, then that probability, let me just draw a line here, is 2 red rocks out of 3. So that would be 2/3. And then the probability of blue is 1 blue rock out of, and this is where the without replacement comes into play. You've removed one of the rocks, so your total number of rocks in the container is not 3 anymore, it's 2. And you still have a blue rock in there, so you're going to get 1/2. So the only way to get to 2, 6 with these 2 numbers is not addition like with the OR, it's going to be multiplication. So that'll give us our 2, 6. And the same thing's happening on the other side, except the probability of the red rock first is still 2/3, but then we put the red rock back and the denominator of the next fraction is still 3, and the probability of a white rock just becomes 1/3. It's 1 out of the 3 rocks that are left in the container. And then this turns into 2 nines. And that is the main difference between without replacement and with replacement. That the denominator in this case is changing, and by the way, the numerator can too, because we're removing a rock from consideration, it reduces the number of outcomes that are left in the container. But if we put the rock back, nothing is changing. So the main thrust of this is the word and, because you're selecting a rock and you are picking another rock. So this word and is going to be equivalent to multiplication. You're going to multiply something. Now, whether it's with replacement or without replacement will let you key in some other information, but the first thing you should realize is you're going to multiply. Alright, so what is the probability of selecting a face card and then a 10 from a standard deck of cards with replacement, or putting the first card back? Okay, so it's going to be an and there's two events going on here. We have a face card event and we have a 10 event. So how many face cards are in a deck of cards? Well, there's the Jack, Queen, and King of 4 suits, so that gives me 12. So the probability of face is going to be 12 out of 52. Okay, and then we're putting the card back after we pick the face card, assuming we're picking the face card. It could be anything, but we're going to put the first card back, and then we're going to see if we can shuffle the deck and pull a 10 next. So that would be the probability of a 10. Well, how many 10s are in a deck of cards? Well, there's 4 of them: hearts, diamonds, clubs, spades. So that would be 4 out of 52. Now, unlike the or statement, where I'd want to keep a common denominator, you can choose to reduce these fractions to make the next step a little bit easier, but you don't have to. Your calculator will do the work for you. So we're going to multiply these. And what's going to happen is, because this is an and, we're going to get 12 times 4. Remember, multiplication between fractions, you go straight across the top. That'll give me 48. And then 52 times 52 is 52 squared. Now, 52 squared is quite a large number. It's bigger than 2,500. I know that much. So it'd probably be best to either change it into a decimal or so it'll probably be best to change it into a decimal or a percent. And I'm not even going to figure out what 52 squared is. It's really not that important. But we get this as a decimal, and it's quite small, so I'm going to change it to a percent because most people are more comfortable that way. So it's about 1.78%. I'll go 2 decimal places. So this is approximately 1.78% of the time you can shuffle a deck of cards, look at a face card, shuffle a deck of cards after putting it back, and then see a 10. So it's not a really high chance of actually seeing this. So what is the probability of 2 cards being dealt at a casino? Sure, why not? Let's go gambling. Giving us a blackjack. Now, for those that don't know, blackjack is an ace and either a 10 card or a face card. Okay, so if the dealer gives you an ace and a 10, you have blackjack and you automatically win. If you have ace and a face card, again, you have blackjack and you automatically win. The thing here is it's a little bit different than the previous example, because when you're dealt 2 cards, this is without replacement. So this one is without replacement. And therefore it is a dependent event. The selection of the first card is going to change the probability of the selection of the second. Now, blackjack, it doesn't matter if you're at a casino and you get the ace first and the 10 second, or the 10 first and the ace second. So that actually becomes an or statement, and I don't want to get into that. So let's look at ace first and the other card second. Okay. So without replacement, if it's ace first and the other card second, and I'm separating them in this way because the other card can be a 10, a jack, a queen, or a king, but one of the cards has to be an ace, so I want to keep him kind of separate. Then if the selection of ace first, there are 4 of them out of 52. Now, once that ace hits the table, it is not put back into the deck of cards. Oh, another little note, casinos don't use one deck of cards, they use upwards of 10 to make these probabilities much more difficult to deal with, but we're going to stick with one deck of cards. All right, when we get to the second one, and we're going to be picking, or the dealer is going to be giving us another card, the and tells me to put a multiplication in there. The ace is sitting on the table, so there are only 51 cards left in the deck. So the number of outcomes has been reduced by 1. And the second card can be a 10 or a face card. Well, how many 10s are in a standard deck is 4. How many face cards there are 12. If we have an or, that means we're going to add them together because it's a face card or a 10. So that's a total of 16. So it's 16 possible cards for the second one. So that would be the probability of an ace first and the other card second. Or, might as well talk about it, it's not that hard. It's the 10 through face card first out of 52 times the 4 aces out of 51. So technically, my 5 here is horrible, 51. So technically, these are equivalent fractions after you multiply them together, because you'll get 4 times 16 in the top and 52 times 51 in the bottom. The order of the multiplication doesn't matter. So this is the same as 2 times 4 over 52 times 51, and then 4 times 16 in the top. All right, so let's see what this is equal to. 2 times 4 over 52 times 16 over 51. Oops, times. It thinks it's a decimal. So this would be the probability of a dealer giving you blackjack right off the bat. So times this by 100 to change it to a percent. So it happens about almost 5% of the time, 4.8. So this would be approximately 4.8% of the time you will be dealt a blackjack. Now, of course, if you increase the number of decks in the cards, then this probability changes completely. But not much. All right, so a container has 5 red rocks, 10 blue rocks, and 3 white rocks. What is the probability without replacement of selecting a red and then a white rock? So here, you have to remember these things. Order is really important. So when we do this, we're going to deal with this and with multiplication, and then we also have to deal with without replacement. So basically we take the rock out and leave it out of the container. All right, so we're going to start off with the probability of red times the probability of white, given that we've already taken a red out of the container. All right, so the probability of red would be 5. There are 5 red rocks in this container out of 3, 10, 5, 18. So this would be 5 out of 18 times. Now remember that red rock is pulled out. So the probability of white would be 3 rocks, which is over here, out of 1 less than 18. So it would be 3 out of 17. So this probability would be 15 divided by whatever the heck 18 times 17 is. So again, about 5%, 4.9%. So this would be approximately 4.9%. Now, a little calculator note, when I typed into my fancy little writing thing, it understands order of operations. So if you were going to type this into your calculator, there's 2 ways of doing it. You can go 15 divided by 18 divided by 17, or better yet, I think it would be better to do 15 divided by parentheses 18 times 17. So it understands that the denominator is both numbers, the 18 and the 17. Now, on a quick little side note, what about the probability of 2 reds in a row? So if I'm looking for the probability of 2 reds without replacement, the probability of red for the first one times the probability of the second one being red, given that, now without replacement, you have to say, given that the first one was already red. So the probability of the first one is red is going to be 5 out of 18. The probability of the second one will be red, given that the first one was already red, meaning it's sitting outside of the container, there's only going to be 4 red rocks left out of 17. So then this turns into 20 divided by 18 times 17. In your calculator, I highly suggest you do this. 18 times 17. And 6.5%. Remember, we have to multiply this by 100. And that's 6.5%. So this is approximately 6.5%. Okay. I bet this has happened to some. You didn't study for the test and you're going to have to guess at each question because you have no clue what's going on. There are 10 multiple choice questions on this test with 4 choices each, A, B, C, and D. What is the probability that you're going to get 100 on this test? So when we do this, we have to kind of break down because you don't see the word and in here. So you kind of have to imagine. You're going to guess on question number 1 and guess on number 2 and guess on number 3 and so forth and so on. So the and is there, it's just kind of hidden. All right, so what is the probability you'll get the first one correct? Well, there's 4 choices. So if you're going to get it right, it's going to be one that is correct out of the 4 choices. So the probability of one of them correct is 1/4. Now, getting it right or wrong, the first question, has no effect on getting the second question right or wrong, assuming that you don't get nervous in between. So that means the probability of each question is going to be 1/4. So then that turns into 1/4 times 1/4 times 1/4, and you're going to have 10 of these 1/4s. That's the same thing as 1/4 raised to the 10th power. These are 10 factors of 1/4 is the same thing as 1/4 raised to the 10th power. So if we type that in our calculator, 1/4, notice parentheses even here is really important, raised to the 10th power. And you'll notice, it's 9.5, so you're thinking, oh, it's pretty high percent, until you get to the end of the number when it says times 10 to the negative 7. On your calculator, it'll say e negative 7, and you have to understand that that's a very small number. So let me come back. 953 e negative 7. 9.53 e negative 7. Make sure I rounded right. 9.54. Because there was a 6 after it. No. 9.54 e negative 7. All right. So this is the decimal percent. So then I'm going to have to come back here and go, let's make it a little bit better, times 100. So then it becomes this number. Now I'm going to still write it as scientific. 1, 2, 3, 4, 5. So this would be 9.54 e negative 5%. Still a really small number. You remember it was 0.1234554%. So this probability of getting 100 on a test. Then we can say, well, what was the probability of not getting 100? Or getting at least one wrong? So, not 100? Or at least one wrong? Now remember, at least one wrong is one wrong or two wrong, all the way up to all 10 of them wrong. Now, from the beginning, we were talking about complements, and this is where they come in handy. This is the probability of getting them all correct. So the complement of all correct is at least one wrong or not getting 100. So then the probability of this event, its complement, put my little dash there, is going to equal 1 minus the probability of the event I found. So in this case, it's going to be 1 minus, and because I'm dealing with 1, I got to deal with the decimal value. So it would be 9.54 e negative 7. If I was going to deal with the percent one, I have to use 100% minus the probability as a percent. All right, so let's go back to my calculator, get rid of the times 100, and subtract this from 1. And notice that the 1 has to be in the front. So this is crazily, that's what I thought, times 100. Oops, I gotta put the whole thing in parentheses. So times 100, 99.999905. So this is equal to 99.99995 percent. Of the time, you'll get at least one wrong by guessing.